Hi, my name is Guang and she's 12 years old. For this lesson, we'll be continuing on with techniques and applications for definite integration. For this lesson of definite integration, we'll be continuing on with this example, whereas we have to find the volume removed when a hole of radius A is bored through a sphere of radius 2A as shown over here. The axis of the hole being a diameter of the sphere. So you may be wondering why do we have the word method over here? Well, it is because we've already had 3 methods before, and for this lesson we'll be continuing on with method 4 and 5. So for the previous 3 methods, on our first method we simply just used the formula for both the cylinder, to find the volume of the cylinder and to find the volume of the 2 caps, the 2 spherical caps. So we kind of just in the spherical cap formula. Well, for our second method, we just decide to take 1/8 of this whole thing, basically the first octant, and since this is about volume, so you don't have to worry about the positive and negatives. So for this part, what you'll have is that we triple integrated the first octant, then after that times 8 to find the full volume. And then our third method simply was cylinder by cylinder, and you find the volume. Well, for our fourth method, which we are going to talk about for this lesson, so for the cylinder, you can straight up just solve it, right? So for the cylinder, how we simply just calculate it by using the base times pi, whereas the base being just a circle, it will be pi r squared times the height. So over here, the r being the a, so it becomes pi a squared times whatever the height is. And then what about for the 2 caps? Well, for the 2 caps, you can use a times 2 because for volume, the positive negative doesn't matter. So for this part, so you times 2, that means you only find one of the caps has first before times 2. So how are we supposed to find one of the caps? We'll use the disk by disk method. So over here, what we'll have for this part is that our volume will be equals to, so what is the volume of the cylinder? So we already had the pi a square. So if you didn't know, so for our first lesson of this example, we have already talked about like what the height of the cylinder is, which is basically 2 square root 3a. So what you're going to have here is 2 square root 3a cubed. Okay. So that will be the volume for the cylinder. Then on the other hand, for the volume of the caps, you just have to plus 2 times. So once again, and over here for this part, just because that it is volume doesn't mean that it just has to be triple integration. We have done this volume with triple integration, yes. We also have done it with double integration, yes. But for this lesson, we're going to do whole single integration for method 4. So over here, what we're going to have here is simply just stacked up circles, which is basically pi rho square dz. So the rho basically depends on the z, okay? And then what will be what is the boundary? So for the z over here, what our height range from is, we basically range from this part till this part, whereas what we will have for our boundary is from square root 3a to 2a, okay? So that will be our boundary, okay? Alright, so for this part, the cylinder part stays the same. Well, for this part over here, what is rho? So depending on which method you use, you get the same answer. So the 2 methods you can use for to find what rho is basically the Pythagoras theorem, or else it will be the intercepting chords theorem. If you're using the Pythagoras theorem, it will simply just be, so over here you have the rho as the radius, right? So over here you have rho for this part, and our height over here is basically j, and this part is basically just a right angle. And what is this? This is always, because it's for the sphere, so this is always 2a. So one way you can do it is by using the Pythagoras theorem, which will have rho squared plus j squared equals to 4a squared, whereas rho squared is equals to 4a squared minus j squared. Or another method, by using the intercepting chords theorem, we can get, so rho squared will be equals to, so over here is basically the two sides, whereas, so just take a quick look before I erase those. And so for the second method, whereas we have the circle, and then after that we have our rho square as shown over here, which we will have the two chords, right? So this part is rho, this part is also rho, so that's how we get the rho squared. So over here is basically this part times this part will be equal to this part times this part. And over here, what are these two parts? So what we'll have is, so for our first part we'll have 2a over here, because that 2a over here is basically the radius for this part. So 2a plus j, which is basically this part. This part is basically 2a plus j. And then this part is basically 2a minus j. So 2a plus j times 2a minus j, and what would, so this is basically a plus b times a minus b, which you will get a squared minus b squared, ultimately a 4 or a squared minus a j squared. Okay, so these are the two ways you can use to find the what rho is. So for this part, you don't need to know what a is, since it is basically just a constant from the question. So just take a quick look and boom. So here you have 4a squared minus j squared dj. And then now that you have gotten this part, what you can do next is that, so what we will have here for the first part is the same, and then over here for this part you can straight up integrate this already, which you will get a 2 pi times bracket 4a squared j minus 1 over 3j cubed from square root 3a to 2a. So over here, now that we have gotten this part and we have integrated, we can substitute the boundaries inside, whereas the first part will be the same. Then over here you substitute this part inside, which you're going to get 8a cubed. And then 8a cubed times 2 pi, you get a 16 pi a cubed. And now you substitute this part inside, whereas you're going to have, so over here you're going to have 3 because of, so square root 3 over here. So square root 3a cubed over here, then you have a 4 square root 3a cubed, then times this part, you minus 8 square root 3 pi a cubed. Then for this, when you substitute this part in, you'll have the minus. So over here, 2a bracket to the power of 3 will be 8 over 3a cubed, which will end up with a 16 over 3 pi a cubed. And then after that, this part, when you substitute this in, negative becomes positive, and you add a, so the 3 square root 3 from the cube over here you simplify as 3, and you get a 2 square root 3 pi a cubed. And now what's going to happen? So over here for this part, what you're going to have, you can combine some parts. So if you put these three parts together, you get a negative 4 square root 3 pi a cubed. Then what about combining these two without the square roots? So what you're going to have here will simply be plus 32 over 3 pi a cubed, which you're going to end up with, taking out the 4 pi a cubed, you're going to end up with 32 over 3 minus, because over here you take out a 4, it becomes 8 over 3 minus square root 3, okay? So, and this is the result that we get. So that is for our first method. So take a quick look before I erase it. Moving on to our next method, we have method 5, outer cylinder by cylinder. So outer cylinder by cylinder is basically just the volume of the sphere, but it minus of the volume of the parts that are not removed. And to find the parts that are not removed, we use the cylinder by cylinder method. While for the sphere, we simply just use the formula. So for this part, so the V, so what's the volume of a sphere? So the volume of a sphere is basically 4 over 3 pi r cubed, right? So for this part, in this case, the r would be here 2a. So it becomes 4 over 3 pi 2a cubed, bracket cube. So now you can take out the 2, whereas you're going to end up with the 8 times 4 being 32 over 3 pi a cubed. So we'll have our 32 over 3 pi a cubed minus of the part that was not removed, which is integral. So first of all, there are two parts, right? So yes, there are two parts, to which we have to separate the top part and the below part. Over here, since we're talking about z, so we can use single integration for this part, whereas we're going to have z. So over here for this part, basically the height times the circumference of the circle, whereas for this part, the circumference of the circle is basically 2 pi r. So let me just erase this r because it's a different r. So the 2 pi r over here, you're going to have a 2 pi r, which is this bigger r. So and then we have dz. So what is our boundary over here? So I mean dr because for the radius. Whoop-de-doo. So for the r, what's our radius over here? Our radius is basically from a to 2a, right? So the front part will stay the same. So what you're going to have here is that, so for this, what is z equals to? So for the previous method, we have used the rho and we used the Pythagoras theorem to get all those, right? Well, for this part, we are once again going to use the Pythagoras theorem. So over here, what we'll have for this part is that, so we have our z over here, and then right angle our r over here, and then what we have over here is always 2a. So for this part, so z squared plus r squared will be equals to 2a squared, which is 4a squared. So z squared will be equals to 4a squared plus minus r squared. And thus, Z will be equal to square root 4a squared minus r squared. So for this part, when you sub it in, so just take a quick look and for this part you have r square root 4a squared minus r squared d r. So how are you supposed to get the negative r squared in order to integrate? So we already had 1r over here, right, which we can put in, which will have a half. We can take a half in front. Then the negative, perfectly, we have a minus in front, which we can change it to positive. And we will have, so for the first term, you will still stay the same, but for this part, it will be a plus, because you put a negative here, and you become a 2 because of the half, which is needed for r to become r squared. And thus it will become d negative r squared. But over here for this part, if you're wondering what happened to here, well, since differentiating here will become 0, so for this part, you can just add it in. So over here, now that we have gotten this, we can integrate already, which we will get. So first term once again doesn't change. Whereas for this term, we will have 2 over 3, because this is basically bracket to the power of 1 over 2. So once you integrate, it becomes 3 over 2, and then here we have the 2 over 3 bracket 4a squared minus r squared from a to a. Whereas when we substitute it inside, what we're going to get here is, so over here we're going to get the 2a, so 2a when you square for this way will end up with a 0. Wait, let me check something. So give me a sec. Oh, whoopsie. So for this one, you have your 3 over 2 over here. So when you sub in the 2a, it will become 0. When you sub in the below part, you have a negative in front. And you have your 4 pi over 3. And then for this part, you have 3a squared bracket to the power of 3 over 2, which will become 3a. So let me just first write this. Then for this part, the a squared will become a cubed, and the 3 will become to the power of 3 square root 3, where we'll have, so in front for now will still stay the same. So over here you'll have simplify the 3, and then after that you can take out the pi, the 4 pi a cubed. And then after that we'll have 8 over 3 to minus square root 3, and that is the result that we get. So that will be all for this lesson, whereas for this example we have already learned 5 methods, and the 5 methods, the 5th method over here, outer cylinder by cylinder, we basically use a sphere's volume to minus out the volume that was not removed. Then for our 4th method, we basically find the cylinder using the formula. Then after that, for the caps, we use disc by disc. And then 3rd method, which is previous lesson, we use a cylinder by cylinder, but it's for the part removed instead. While for our 2nd method, once again last lesson, and what we had was to use triple integration on the first octant, and then times 8 to find the total volume. Then our first method, which is the first lesson for this example, what we used was just the spherical cap formula, and that's pretty much it. So that'll be all for this lesson. Last but not least, thank you for your watching.